Hello and welcome to another lecture based on applications of derivatives. Today we shall be finding out the slopes of the tangent and the normal to a given curve. Later we are going to find the equations of tangents and normals, and finally we shall conclude this lecture based on applications of derivatives by discussing some numerical problems that would be based on finding the slopes and equations of the tangents and normals on the given curves. Now we are going to begin this lecture by discussing the slopes of the tangents and the normals that are drawn to the given curve. First of all, let us consider slopes of the tangent and the normal. So starting with the slope of the tangent, we are going to start with this graph which has a curve y equal to fx, and to this curve we have drawn a tangent which touches the curve at point P, which has coordinate x1 and y1, and the normal drawn to this curve is as shown, which also touches this curve at point P whose coordinates are x1 and y1 again. And this is the angle which the tangent makes with the positive x-axis of this graph. And thus we can define the slope of the tangent by considering a curve which is y equal to fx, which is continuous in nature, and point P, x1, y1 coordinates of P be the point on it. Then the slope of the tangent to the curve y equal to fx at point P is equal to dy by dx at P equal to tan of psi, where psi represents the angle that this tangent makes with the positive axis of this graph. Here, if the tangent at P is parallel to x-axis, then the value of psi is equal to 0, which implies that tan psi would be equal to 0, which further implies that the slope, which can be represented as m, is equal to 0, which further implies that dy by dx at point P is equal to 0. Whereas if the tangent is perpendicular to the x-axis, then psi would be equal to pi by 2, which implies that cot psi is equal to 0, which further implies that 1 by tan psi is equal to 0. This implies that dx by dy at point P is equal to 0. Thus, if the tangent is parallel, then psi equal to 0, and thus we have the slope of that tangent equal to 0. And if psi is equal to pi by 2, that means the tangent is perpendicular to the x-axis, then dx by dy at point P is equal to 0. Next, we are going to discuss the slope of the normal. As discussed in the previous section of this lecture, the normal was the line that was drawn onto the curve at point P with coordinates x1 and y1 and was perpendicular to the tangent at point P and passing through P. Therefore, the slope of the normal at P is equal to minus 1 divided by slope of tangent at P, which is equal to minus 1 divided by dy by dx at point P, which can be written as minus dx by dy at point P. Thus the slope of the normal at point P is given as the negative of 1 divided by slope of the tangent at P, which is equal to minus dx by dy at point P. Next we are going to discuss the equations of the tangent and normal, and thus we are going to find how we can use the derivatives in finding the equations of the tangents and the normals. We know that the equation of a line passing through a point with coordinates x1, y1 and having a slope m is given as y minus y1 equal to m x minus x1. Now we have already discussed that the slopes of the tangents and the normals to the curve y equal to fx at a point P with coordinate x1 and y1 are given as dy by dx at point P and minus of dx by dy at point P respectively. Therefore, the equation of the tangent at point P with coordinates x1 and y1 to the curve y equal to fx is given as y minus y1 is equal to dy by dx at point P into x minus x1. Now since normal to the point with coordinate x1, y1 passes through P and has a slope as discussed is equal to minus dx by dy at point P, therefore equation of the normal to the curve fx is given as y minus y1 equal to minus 1 divided by dy by dx at P into x minus x1, where we have converted the slope of the normal which was discussed to be minus dx by dy at point P as 1 divided by dy by dx at point P. Here, if dy by dx at point P is equal to infinity, then the tangent at point x1 y1 is parallel to y-axis and its equation is equal to x equal to x1, and if dy by dx at point P is equal to 0, then the normal at point P with coordinates x1 y1 is parallel to y-axis and its equation is given as x equal to x1. Now we are going to discuss a problem that would be based on finding the equations of the normal or the tangent to the given curve. Here we have a problem in which we are required to find the equation of the tangent to the curve y equal to minus 5x square plus 6x plus 7 at point whose coordinates are 1 by 2 and 35 by 4. Now here the equation of the given curve is equal to y equal to minus 5x square plus 6x plus 7. This implies that the value of dy by dx is obtained by differentiating this equation with respect to x. Thus we have dy by dx equal to minus 10x plus 6. Next we are going to find the value of dy by dx at the given point whose coordinates are 1 by 2 and 35 by 4. Thus dy by dx at point P with coordinates 1 by 2 and 35 by 4 is equal to minus 10 by 2 plus 6, which is equal to 1. Now we know that the required equation of the tangent at the given point with coordinates 1 by 2 and 35 by 4 is given as y minus y1 equal to dy by dx at point P into x minus x1, and thus we have the equation as y minus 35 by 4 equal to dy by dx at point whose coordinates are 1 by 2 and 35 by 4 into x minus 1 by 2, which implies that the required equation is equal to y minus 35 by 4 equal to m into x minus 1 by 2. Since the value of dy by dx at the given point is found to be 1, therefore we have equation as y minus 35 by 4 equal to 1 into x minus 1 by 2, which can be simplified and rewritten as y equal to x plus 33 by 4. Thus we have found the equation of the tangent to the given curve at the given point. With this we conclude the lecture on applications of derivatives that was based on the tangents and normals.